cotangent functions. And really, there's a lot of memorization going on in here, and once you get comfortable with kind of the shortcuts to taking the derivative of these trig functions, then you'll be rolling right along in pretty good shape. Okay. Derivative of trig functions. Okay, and you will need to memorize these, especially the sine, the cosine, the tangent. When you then get into the cofunctions like the secant and the cotangent and the cosecant, we don't use those quite as frequently, but you really got to nail these other ones. Okay, so here are the derivatives that you might need to write them on a card or something and keep them close at hand as you're moving through your homework. And then, like I said, when you work enough homework problems, this will become just second nature to you, be no problem. So, for instance, the first derivative, or d dx of sine x, the derivative of sine x is cosine x. Very simple. The derivative of the sine function is the cosine function. The derivative of the cosine function is the negative of the sine function. Okay, so the derivative of the cosine is a negative sine function. The derivative of the tangent function is secant squared x. The derivative of tan x is secant squared x. And those three you will use over and over and over and over again. Then the other ones that we have here, we do use them. I don't know these by heart like I should. This one I know pretty good. The derivative of the secant function is secant x tan x, and we do use that one off and on. The derivative of the cotangent function, this one I'd probably always have to go to my book to recall. This is the cotangent, C-O-T, cotangent function is a negative cosecant squared x. And the derivative of the cosecant x function is negative cosecant x cotangent x. And that one, I guarantee you, I don't know that one by heart. Okay, so there are the 6. Now, how in the world did they ever come up with this? I'll show you very quickly and very briefly. They actually derive these. They go ahead and use that limit as h is approaching 0 of f of x plus h minus f of x over h as h is approaching 0. They do this, and it's really not as complex as you would think it would be. So just briefly, I'm going to show you one of them. Pull it up in the book. And I won't expect you to do this, but I just want you to kind of see how it is done. Because it's a lot simpler than you would probably think it would be. For instance, this is on page 135. If your f of x is sine x, and we know the derivative of the sine x is cosine x, the way they derive that formula that we're going to have memorized is, here it is, the limit as h approaches 0, and instead of saying f of x plus h, it'd be sine of x plus h. Well, sine of x plus h, if you remember your sine of a sum of angles, is this. Okay, and then they come in here and they factor out sine of x. Okay, and then they split it. They kind of take the first half of the fraction and the second half of the fraction using their limit laws. And then coming down here, we know the limit of this is 1. I think that this somewhere in the book was a limit of 0 as like a formula. And then they come up with cosine x. And they do this for all of these. Okay, and like I said, it's not that difficult. It would take a little while to figure it out if you ever try to do it on your own. But they do it for all of these trig functions, and it's not as complex as it sounds, but it's just going right back to the foundation of finding the derivative using the limit. Okay, so we're going to go in and do some examples. And like I said, you need to kind of keep these close at hand, because as I go through these, we'll use these repeatedly in taking these derivatives. So this is not difficult. The sooner you get those in your head, the easier these will be. So the question will say, find dy dx, which is the same thing as finding y prime. And then your question is y, or your function is y equaling 3 over x plus 5 sine of x. And so you're going to start seeing the trig functions in these equations where they're asking you to take the derivative. So to take the derivative, I really think I would immediately rewrite that as 3x to the negative 1 power, which would make it a lot easier to use the product, or not the product rule, but the power rule derivative. And so your first derivative would be negative 1 times 3, which is negative 3, x to the exponent of negative 1 minus 1, which is a negative 2. And then this one would really be the constant rule, where the 5 comes out, and then you take the derivative of sine x. So the 5 is the constant that comes out front, and then the derivative of sine x we just discovered, or we're just told, is cosine x. And so then to go ahead and write your answer, and remember y prime is the same as dy dx, would be negative 3 over x squared plus 5 cosine x. It's just that simple. Nothing tricky. Just takes a little practice. Of course, they're going to get a little more difficult, and it just takes some practice. It's kind of fun. Okay, so let's do some more examples. This is all about practicing, getting comfortable in taking these derivatives of these trig functions. So here comes another one. Suppose they ask me again to find dy dx, and they say that y this time is x squared cosine x. Now this is a product, the x squared times cosine x. So you're going to need to use the product rule, first times the derivative of the second plus the second times the derivative of the first. So again, if this were a number like 5, you wouldn't have to do it. But the variable is here, which means you must apply the product rule, where this is the first term and the second term in the product. So when we compute the first derivative, it's the first times the derivative of the second plus the second times the derivative of the first. Well, the first is x squared, and the derivative of cosine x is a negative sine x. Okay, so this is x squared times the negative sine x, and then the second times the derivative of the first is cosine x, and the derivative of 2x, or the derivative of x squared, is 2x. Maybe I should put this in parentheses. That 2x is not times the argument of the cosine function. Okay, this is not x times 2x, which is 2x squared. That is not the way it works. So that's why I'm really going to put the parentheses in to be able to clarify that for you. So this is just a negative x squared sine x plus 2x cosine x is the first derivative of that function. Be really careful. There might be a natural tendency to put the x times the 2x and call this cosine 2x squared, and that is not right. The 2x goes out front of the function. Don't make that mistake. Be certain you get that straight very quickly. Okay, again, find dy dx, where y equals sine of x plus cosine x times secant x. Now, this is another product, okay, where your first is this binomial and your second is the secant x. Your first is the binomial and your second is the secant x. So when I come in here to take the derivative, it'll be the first times the derivative of the second plus the second times the derivative of the first. Well, the first is sine x plus cosine x, and the derivative of secant x, isn't that tan x squared? Tan squared x? No, it's secant x tan x. Okay, the derivative of the second, I don't have enough room here, is secant x tan x. I did not give myself enough room. Plus, I'll just come down. The second times the derivative of the first. Well, the derivative of secant x, again, is secant x times, no, it's not. The second is just secant x, just write it down. And the derivative of the first, I guess I'll put this in parentheses. The derivative of the first is the derivative of the sine x plus cosine x, the derivative of this. The derivative of sine x is cosine x, and the derivative of cosine x is a negative sine x. There, I got it to fit on the page. Okay, so this is the second, and this is the derivative of the first. I just didn't have enough room. Okay, I just didn't have enough room. So I'm going to shift left here and write all this down. Okay, I'm going to shift left a little bit. So now what I'm going to do, I've taken the derivative. I'm going to try to clean it up. I'm going to take secant x tan x times sine x and secant x tan x times cosine x. And I hope I've given myself enough room. So this will become secant x tan x sine x plus, I don't have enough room, secant x tan x cosine x. And then the bottom, when I distribute the secant x, will be secant x cosine x minus secant x sine x. And regardless of what I do, I can't have enough room on this piece of paper. I'm still having to drop a line. Okay, well, let's take a look at this. There's 1, 2, 3, 4 terms. Okay, see it in 4 parts. 1, 2, 3, 4 parts. Okay, the first one, I'm going to move left again. I'm getting ready to make this fit on one line or else. Okay, secant x is 1 over cosine x. Because I know that sine over cosine is tangent, and this is going to become tan squared x. Okay, the second function, let's see, secant is 1 over cosine, the cosines will cancel, okay. The second function, secant x is 1 over cosine x. And then this will be tan x cosine x. This is not going to fit. Okay, and these cosines eventually will cancel. You think I can make it go? Maybe I'll just... Okay, secant x, I'll write really little, is 1 over cosine x. Yeah, I'm going to make this happen. Okay, and secant x again is 1 over cosine x, sine x. It's going to fit on this line or else, okay? Okay, and again, visually, when you look at this, this is your first term, this is your second term, first term, second term, third term, fourth term. Here's the plus sign between the first two, the plus sign between the second two, the subtraction between the last two. Okay, so now in the first one, sine over cosine is tangent, so this is tangent times tangent, which is tangent squared x. The second one, the cosines will reduce, leaving just a tangent x. The third one, the cosines reduce, leaving just a 1. And the last one, sine over cosine, is tangent. Cool. What is tangent squared plus 1? Secant squared. There you go. So this becomes tangent squared x. These guys zero out, so tangent squared x plus 1, which is secant squared x. So there it is.
Keep that in mind if I ever see another sine plus cosine x.
Okay.
Derivative, I'll just be like, wait, no, wait. Let's do this quickly.
It's a trig identity.
Right, and that's an identity that I don't keep memorized, but I know it because, watch me go to the chalkboard. I cannot go to the chalkboard because then the recording is worthless. Okay. Okay, here's the trick. I guess I can fit it here. Okay. Here's a little bit of a trick. You know that sine squared x plus cosine squared x equals 1, right?
Yep.
Well, you have a couple of options here. If you were to divide everything by sine squared x, right? Then this would become what? 1 plus tan squared x equal, is that right? 1 plus cotan squared x would equal cosecant squared x. But if you take it and divide it by, I don't ever have these memorized. These are the ones I just kind of kept the pattern in my head. If I divide them all by cosine squared x, right, then you get tan squared x, which is what we had, plus 1 equaling secant squared x, which is what the identity we just used in this last step. So if you don't have those memorized, it's okay. You can very quickly generate them, without a whole lot of necessary time or effort. I guess I could have written this. This is what? 1 plus cotan squared x equaling 1 over sine is cosecant squared x, and this one is tan squared x plus 1 equaling secant squared x. So there's kind of how you generate those extra identities that seem to come up at the strangest of times, and you have to try to recall something you've not seen possibly in a year or two or more, or 20 years, or 25 years. How long has it been since I graduated from college? Okay, so that'll kind of give you a little bit of a heads up on that one. I'm afraid to cover those up. Okay, so let's take a look at another one. These are just kind of fun. No, they are kind of fun. It's kind of neat how they, where they go. It's like, how in the world? You wonder if, the person who authored the book or wrote the problem just stumbled across it, or how many hours of their boring life they spent trying to come up with a good one. Okay. All right, so we need to take the derivative of this one. And, you could use the quotient rule, or you could use the product rule by using negative exponents, but I don't know. If you take 1 over cosine, what is that? Secant x, it could be x secant x, this could be x to the negative 1. We could do it either way. That is true, but the next one's the product rule. So you know what? I think I'm going to use the lousy quotient rule. Okay, here we go. Okay, bottom times derivative of the top. This is just the first one. The bottom times the derivative of the top is x, and the derivative of cosine is negative sine x. That's the bottom times the derivative of the top, minus the top, which is cosine x, times the derivative of the bottom, which is the derivative of 1. No, the derivative of x, which is 1. Bottom times the derivative of the top, minus top times the derivative of the bottom, divided by the bottom squared, which is x squared. That's the first one. Okay, that's the derivative of cosine x over x. Okay, the second one is going to be the bottom times the derivative of the top. The bottom is cosine x, and the derivative of the top is 1. Minus the top, which is x, times the derivative of the bottom, and the derivative of cosine is a negative sine. Did I do something wrong? No. Okay. Divided by, I don't think this one comes out really nice. Divided by the bottom squared. Yeah, this one doesn't come out to anything fancy, yeah. Actually, I started working this problem. I did go through all the trouble of getting a common denominator, and they didn't go that far with their answer at all. They didn't do all that. So then this becomes what? Negative x sine x minus cosine x over x squared plus, this is cosine x plus x sine x over cosine squared x. Now if you did collect these together with the new denominator of x squared cosine squared x, it just wouldn't accomplish anything. Right. This one I did it in my notes, and I looked at the answer in the back and thought, well, I just wasted a whole bunch of time. So we will stop there. Okay. That actually is the answer, because I looked in the back of the book in the solution to see how far do I take this lousy thing. And so that's the pits, because I don't know how you are going to know in my math lab whether to keep going or not. That's not going to be a good thing. Okay. Right. How far do you want me to simplify this sucker, right? So, okay, so let's go into another product rule. Let's do x cubed sine of x, cosine of x. They want me to take the first derivative of that. Now here, you really have what I call three pieces, or three functions kind of being a product of three, where you have x cubed, sine x, and cosine x. So how do you do the product of three? Well, to do the product of three, you create a product of two, and maybe you let this one be the first, and this be the second. So first times the derivative of the second plus second times the derivative of the first. And when you take the derivative of the first, you have another product rule. Okay, so just kind of think about this mentally for a second. When I come in here and I do the first times the derivative of the second, that's fine. But then when I do the second times the derivative of the first, what's the derivative of the first going to be? An application of the product rule. So you're going to have a nested product rule inside the product rule. Okay? All right, so the first times the derivative of the second. The first is x cubed sine x, and the derivative of the second is the derivative of cosine x, which is a negative sine x. That's not so bad. Plus the second times the derivative of the first. Well, the second is cosine x, but the first is the derivative of x cubed sine x, which is another product rule. So inside here, this is another product rule. So this one's another first and second nested. So I don't know how to do this. This is the first times the derivative of the second again, plus the second times the derivative of the first, where the first is x cubed. So it's the first, which is x cubed, times the derivative of the second, which is cosine x, plus the second, which is sine x, times the derivative of the first, which is 3x squared. So this is the product rule nested inside the product rule of the original function. Okay, so nesting of the product rules. And now let's just see if it cleans up. So this becomes a negative x cubed sine squared x. And over here, we got a mess, okay? Distribute the cosine x. So cosine x times x cubed cosine x is x cubed cosine squared x. And then distributing it again, you get 3x squared cosine x sine x. Not when it's a product, it has to be a quotient. It has to be sine x over cosine x to be the tangent. So, yeah, you're talking about here then? You almost could make a sine squared x. You see, if you factor out a negative x cubed out of the first one, you wouldn't get sine squared x plus cosine squared x equaling 1, because it's a difference instead of a sum. So I don't see anything going on here. I think that's it. But that's the first thought, is can I factor an x cubed out of the first two and come up with a tangent, or come up with a 1, and you can't. So that's it. It doesn't get any better. That's as far as it goes. Okay, this one's actually not very hard. It's kind of neat. Suppose you have sine x plus cosine x over cosine x. Now, there's definitely two ways of doing this one. Your first thought is probably the quotient rule. The bottom times the derivative of the top minus top times the derivative of the bottom divided by the bottom squared. But can you see something else here? Yes, right. Before taking the derivative, if I write this as sine x over cosine x plus cosine x over cosine x, which we can do that, then that is tangent x plus 1, which is a lot easier to take the derivative of than doing the bottom times the derivative of the top, times top times the derivative of the bottom, and then cosine squared in the denominator, and then no tellings what all you would have going on there. Or you get, well, the first derivative, right? The derivative of tangent is secant squared x, and the derivative of 1 is 0, so the answer is just secant squared x.
I was going to say, I already knew the answer because...
Oh, Matt, listen to me!
Because instead of distributing it like that, I just took the cosine and called it a secant and said sine x plus cosine x times...
Yeah.
as that
1 over
third
cosine
one.
is secant, and sine
then I
times
just
secant.
said, well, I already did all the work. Secant squared x.
Almost. Secant sine plus 1 and secant times sine. How'd you do that? It would just be,
If you take what's in the top and put it in parentheses,
yeah.
and then take what's in the bottom
Mm-hmm.
and reciprocate it, then
Right.
it becomes a secant.
Right, so it makes secant x times the numerator.
Yeah, and secant x times the numerator is the same thing
As tangent
that
x
third
plus 1.
example that we did.
Yeah.
You go-
Oh, so you backed up to, so,
I
okay.
said, okay, well,
I see. So you backed up to another question we had already, okay, gotcha. Okay. All right, now here's finally a pretty good question. And it says, graph the curve and the tangent line to the curve. Graph the curve and the tangent line to the curve. Okay, where? Oh, at, this is good. We've got a little more information than this, people. Okay, at x equaling 3 pi halves. They say, wait a second, it's going to have a little more information than this. Okay, so the curve, the original curve, is y equaling 1 plus cosine x. So they want me to graph that curve, and then they want me to graph the tangent line to the curve at 3 pi halves. So we've got to find the equation of the tangent line at 3 pi halves and then graph it. So what does the graph look like of 1 plus cosine x? Well, that's cosine x lifted 1, right? Y'all agree? Is cosine x up 1? Okay, so we're up 1. So let's go, how big do I want to go with this? 3 pi halves, 2 pi halves, 3 pi halves, 4 pi halves. Okay, so this would be pi halves, pi, 3 pi halves, 2 pi, and I guess we should go in reverse just like that. Okay, so remember, this is the cosine curve up 1 unit because of the 1 plus it. So if we're right here, and if this is 1, and then this up here is 2, so if that's the case, we're jumping at 1. Make certain I get this right. So we're going to come down. Oh, yeah! See if I can do it. Here's my, here. I have to do this. Okay, now I can do it. I think. I've got to return to this height. I'm going to go down here. Here we go. Okay. I'm going to go down here, back up there. Ooh, that's a good one. I did that well. And again, down, across here, and no, go through the little square. Okay, right there. Okay, there it is. Okay, there's the y equaling 1 plus cosine x. So it has an amplitude of 1, but it jumped 1. So there it is. Okay, so now, if we're going to find this stuff going on at 3 pi halves, we want to know this tangent line right here at 3 pi halves, which looks something like this. Am I going to miss it? No, okay, I got it. Something like that. Graph the curve. Well, I just graphed it. Let's get the equation of it too. Let's get the equation of it. Okay, if I want to know the equation of this pink tangent line, then I need to know a point, and I have a point, or I can get a point, 3 pi halves and something, and I need the slope, right? I need the slope of the tangent line when x is 3 pi halves. Those are the two things I must have to get the equation of that tangent line. So at 3 pi halves, what is this ordered pair? 3 pi halves and 1 plus cosine of 3 pi halves. What is cosine of 3 pi halves? Well, 3 pi halves is right? Here's pi halves, 2 pi halves, 3 pi halves right here, right? Okay, so cosine of 3 pi halves is 0, so 1 plus 0 is 1. So there's this ordered pair, which is beautifully graphed. I could have just taken it off the graph, right? A height of 1. So now what is the slope of the tangent line? How do I get this? Come on, calculus students. The first derivative, right? The first derivative is going to give me an expression, and I got to throw the x value of 3 pi halves into it. So here this is the same thing as saying y prime when x is 3 pi halves. That's the same notation, okay? So we need to figure out what is y prime. What is the first derivative? Well, y equals 1 plus cosine x, so the first derivative is 0, and the derivative of cosine x is negative sine x, right? So the first derivative is a negative sine x. Now that's the expression that's going to tell me the slope of the tangent line anywhere on that curve, but I very selectively want to know its value at 3 pi halves. So the slope at 3 pi halves, this is the same thing as the slope at 3 pi halves to this curve, okay, is a negative sine of 3 pi halves, which is a negative times something. Well, sine of 3 pi halves is what? Negative 1. So this is 1. So if we want the equation of that pink line, which is the tangent line to the curve, here is my point, and my slope now is 1. So I just have to find the equation of this line, get back on the screen, that goes through this slope and this point. So y minus y1 equals m times x minus x1. Y minus 1 equals a slope of 1 times x minus 3 pi halves. So y equals x minus 3 pi halves plus 1, whatever that is, x plus some number. No, x minus some number. But this is the equation of the pink line, which is the tangent line to the curve. The equation of the tangent line at x equaling 3 pi halves. It looks kind of weird, doesn't it? We don't normally see an equation that looks like that. But remember, 3 pi halves is just some decimal, right? Plus 1. So it's just a number. That's pretty cool. And we could graph that on the calculator, too, if y'all wanted to see it. Time-wise, how are we doing? We could. See if I can figure out how to get it on the screen. And I don't have my smart view up, so I'm just going to pull up this virtual. Let's see how it looks, if it's going to be big enough. Come on, virtual. Usually it opens very fast. Where is it? I'm a little bit impatient this morning. Okay, here we go. I thought I already cleared that off of there. Okay, so this is 1 plus cosine x. This is my original curve. X. And I'm just going to do a zoom trig, which should take me from negative 2 pi to 2 pi, which is what we did. There it is. That's what we did. And then if I want to get the tangent line to the curve, that pink one, look, there it is. We're right beside it. This looks good. We came up with y equaling x minus, I'm going to put this in parentheses just for the sake of doing it. No, I can't put it in parentheses. Go back. I cannot do that. That would not be right. Okay, so this is what, I have to put this one in. 3 pi halves, 3 pi halves plus 1. Oh, maybe we want to animate this one. It'd be kind of cool. Get there. Grab it. Here it comes. There's my pink line. Right through that one little point. Perfect tangent line. Isn't that cool? Doesn't that make you feel confident that you know what you're doing? Okay. That should make you feel good. Okay? All right. So, we should be happy. That's the end of this section, but we're going to move on to the next one. So let me close this recording. If the screen would come to the desktop. That was confusing.